Hello from AI Sciences and welcome to Backpropagation Explained for Beginners. I'm your instructor Kashif Murtaza, and in this video we are going to talk about backpropagation. Because this algorithm backpropagation or the method backpropagation works typically in neural networks, it will be great if we just spend a couple of minutes on talking about what are neural networks, what do we mean by forward pass in neural networks, and for training, what do we mean by gradient descent. So let's dive in and see what are artificial neural networks, what is forward pass, what is gradient descent, and after knowing all these things, we will be equipped with understanding what do we mean by backpropagation. So artificial neural networks or neural networks are basically consist of several neurons or computation units. For example, you can see a computation unit here. That's a computation unit. That's a computation unit. This X is an input, and here we are supplying this X as input to this neuron, and the same input is going towards this neuron. This parameter, this W1 is parameter of this neuron. This B1 is sometimes called the bias for this neuron. Similarly, W2 is parameter for this particular neuron, and B2 is the bias parameter for this neuron. This neuron does some computation on the inputs and the values of parameters, and then this F1 is some activation function that is applied, and after applying this activation function on this particular value computed by the inputs and the parameters, the output of this neuron is A1. Now this output, similarly the output of this particular neuron is A2. These outputs are supplied towards the next layer of neurons or the computation units. Now this A1 is a real number, and this W3 is parameter for this particular neuron. B3 is a parameter for this particular neuron. But this neuron actually is seeing A1 as well as A2 as two inputs rather than just one input. Each input is carrying its own parameter with it. So this W6 is also the parameter for this particular neuron. W3 is the parameter for this neuron. A1 and A2 are acting like inputs towards this neuron. And B3 is the bias parameter. Similarly, for this particular neuron, A1 and A2 are again acting as inputs, and W5 and W4, they are acting as weight parameters. And this B4 is the bias parameter. And these F1, F2, F3, F4, these are all activation functions. Similarly, this neuron is giving A3 as output, and this particular neuron is giving A4 as output. And this particular final neuron has parameters W7, W8, and B5 as a bias parameter. The output of this neuron, we are writing that as Y hat, is actually the prediction, and this Y is the ground truth, and this L is some loss function that actually can be computed by having this Y hat, the prediction from the neural network, and the actual value Y. So that's the architecture of artificial neural network. Obviously, in each layer, the number of neurons can vary and the total number of layers can vary. The types of activation functions can vary, and this X can be a vector input, where in that case, this W1 will be a vector, W2 will be a corresponding vector, and so on. So there are a lot of, lot of variations in designing the architecture of a neural network. Next, we see the forward pass in a neural network, and we are going to see this by an example. So let's take an example how this value Y hat is computed. So for that, let's take certain examples. Let's say all the activation functions, F1, F2, F3, all the activation functions, let's say they are ReLU activation functions. And by ReLU, I mean this max of 0 and Z. So let's say F1 is ReLU, F2 is ReLU, F3 is ReLU, F5 is ReLU, and so on. And let's say this Z value is the value that is inside here. So let's say this value is Z1. That particular value is, let's say, Z2. Similarly, we have Z4 value, which is this value. So the value on which the activation function is going to be applied, let's call these values as Z values. So let's say this is Z4. This value is Z3. 3. Similarly, this particular value inside, let's say this is called Z5. We are taking ReLU function because it is simple, and further it is mostly useful. Let's say all these activation functions are ReLU. Let's say our loss function is squared loss, which means loss function on y hat and y. Let's say that's a squared loss function, which means y minus y whole square. Let's say that's our, or 1 by 2, just to avoid this, the term 2 that will appear here at the differentiation time. And further, assume all the weights, W1, W2, W till W8, all these parameters, weight parameters, all these are just 1, let's say. And all the bias parameters, let's say B1, B2, B3, all these bias parameters, let's say Bj, these are all -1. And assume that the input value x is, let's say 10, and we want to produce the output value y. Let's say y is, let's say we want to produce 1 here. So let's see how the forward pass works. So let's compute the Z1 value first. So Z1 is basically, W1 is 1, all the weights are, let's say 1, all the biases are -1. So W1 is 1, 1 times 10, -1, this -1, that is 9, and 9 is greater than 0. So Z1 is, Z1 basically is 9, and A1 is also 9. So consequently, A1 is also 9. Similarly, we can compute Z2. Z2 is also, in this particular case, 9, and A2 is also 9. Now let's go to compute Z3. Z3 can be actually computed by A1 times W3 plus A2 times W6, because initially all the weights are 1. So we have this 9 plus 9 minus 1, which is 17. So Z3 is 17, and consequently A3 is 17. And similarly, this Z4 is 17, and so A4 is 17. Now A3 is 17, A4 is 17, so Z5 can be computed as, Z5 is basically 17 plus 17 minus 1, because all the biases, we set all the initial biases as -1. So 17 plus 17, 34, minus 1, 33. So Z3 is 33. And so this value, which could be called as A5 now, but we are calling it as y hat. Y hat is 33 because 33 is bigger than 0. So that, but we really wanted to predict y as 1, and we end up computing y hat as 33. So what we really want is to set these parameters, W1, W2, B1, all these parameters, to set these parameters so that the output is closer to 1, which right now with the current setting of parameters, that value is 33. Think, for example, by changing no other parameter, just change this W7, let's say. If you change this W7, let's say to -1 rather than 1, then A3 times -1, which is -17, plus 17 minus 1, the overall value Z5 could be -1 in that case. And -1, once go through ReLU, the y hat could be 0. And 0 here is more closer to 1 rather than 33. That means by selecting appropriate values of these parameters, we can come up with the prediction that is closer to the ground truth. But nonetheless, that's the forward pass. Forward pass requires to have the definition of loss function, the definition of all the activation functions. All the activation functions may be different. You need to have the initial values of the parameters. They need not all be the same. They may be different. Once having all these things available, the input can progress forwardly and make a prediction, and that is known as a forward pass. We will get back to this forward pass later when we will see the backward pass, or sometimes known as backpropagation. Now, how can we select these values, W1, W2, W3, all these values, to minimize our loss? Loss is actually the deviation or the difference between the predicted value and the ground truth. How can we select these parameters such that the loss is as minimum as possible? So the algorithm used for that is gradient descent, which tells that given a particular value of the loss in the parameter space, one can step in the direction negative to the gradient of the loss function. And that step, let's say alpha step, sometimes known as the learning rate, if you take the step alpha in the negative of the gradient direction, then you can reach to a better parameter, or the parameter that has loss value smaller than the previous parameters. So if we want to update W1, so let's say this is the new value of W1. The new value of W1 is equal to the old value of W1. In our case, that is 1 plus alpha times the negative gradient, negative derivative of loss function with respect to W1. So, and we need to update all the parameters. In our case, all the parameters are W1 to W8, and then all the parameters B1 to B5. If we want to compute the update for all these parameters, we have to compute the derivative with each and every parameter, and then we have to take a step in the gradient direction, negative gradient direction. That's cool. That means if we want really an updated value of W1, we need to compute the derivative of the loss function with respect to W1. And if we want the updated value of W2, we need to compute the derivative of the loss function with respect to W2. No matter what parameter you are going to update, you have to compute the derivative of the loss function with respect to that parameter. But here is a problem: how you are going to compute the derivative of the loss function that is way, way deeper in the right-hand side with respect to W1. How can you do that? Well, one way is to apply a chain rule. For example, let's update W7 first, which will require the derivative with respect to W7, and then let's update W8, which will require the derivative with respect to W8. Now, once we have derivative with respect to W7 and W8, maybe that information can be backpropagated to compute the derivative with respect to W1 and W2. So essentially, that's the idea of backward pass or backpropagation. You compute the loss function, which is the error, and somehow backpropagate that error through gradients, step by step, just like the forward pass. Just make a backward pass to update all the parameters, and particularly the parameters in the very initial layers. And that requires chain rule, basically. Let me explain how it will be done. So what will happen is the following. First of all, the derivative with respect to y hat will be computed. So let's say the derivative of the loss. Let's compute the derivative with respect to y hat. Now the derivative with respect to y hat is available. Now literally, y hat is essentially this particular value, which is the, let me call that value as Z5. And that's particularly the value Z5 when we apply a ReLU function or any activation function on this Z5. So if y hat indeed was positive, that means Z5 was positive, and in that case the derivative is simply 1, otherwise the derivative is 0. So in any case, we have now the derivative with respect to y hat. Now if we want to compute, for example, the derivative with respect to W7, the derivative of the loss with respect to W7 is essentially, what we are going to say is that how W7 impacts our loss function. Well, that means how W7 impacts y hat, and then in turn how y hat impacts our loss function. That's a simple chain rule. And if you focus here, if you already have computed this quantity, you can plug in that quantity here and you can compute this quantity, no problem. You already have all these values available and you can compute this quantity. Now similarly, you can compute the derivative with respect to A3. Similarly, you can compute the derivative with respect to W8 and derivative of the loss function with respect to A4. Now the next step is, how can we compute the derivative with respect to W3? Well, to compute the derivative with respect to W3, you may ask how W3 impacts Z3, and then in turn how Z3 impacts this A7 or the derivative. So that can be computed again using the chain rule, and through this chain rule, here you will be having derivative with respect to W3 as well as derivative with respect to A1. Similarly, derivative with respect to W6 and derivative with respect to A2, derivative with respect to W5 and W4. All these derivatives of the loss function will be available. Now you are ready to compute the derivative with respect to W1. How W1 impacts Z1, and then in turn how Z1 impacts A1. And similarly, A1 impacts the loss function through two routes. One route is this to impact the loss function. The other route is this to impact the loss function. So that will give again the derivative with respect to W1 and similarly the derivative with respect to W2. Once you have all the derivatives available, you apply your gradient descent update and then you apply forward pass again. But what is important here is that the gradient or the error information at the very end propagates back through chain rule to each and every parameter back in every layer. And that precisely is known as backpropagation, or you can call it as a backward pass. After the backward pass, you'll be having updated values of all the parameters. Then you will apply the forward pass with updated parameters and you will get a loss value which will be smaller than the earlier lost value with the earlier parameters. After getting that loss, you can again apply the backward pass or backpropagation and update the parameters and go back and forth until you get a loss value that is really acceptable or great. So that's the very high level overview of backpropagation. Backpropagation cannot be explained without forward propagation. That's why I introduced the forward propagation at the first place, and I also went through a very simple example. But that's basically the idea behind backpropagation, and that's the key algorithm used for training neural networks. So I hope you have liked this video. Please press the like button, subscribe our channel, and share this video with your friends. Hope to see you next time.